NVIDIA has recently introduced Eureka, an AI robotic entity showcasing unprecedented agility, capable of performing tasks such as opening drawers, intercepting balls mid-flight, and manipulating a pencil with its mechanical digits, activities once thought to be exclusive to human dexterity. Eureka's remarkable capabilities will be further discussed through three pioneering aspects and how it integrates with OpenAI. Firstly, Eureka benefits from NVIDIA Research's advanced simulation environment, which propels the training process to remarkable new speeds, 1,000 times faster than conventional methods. In this virtual setting, 10 distinct robots have been trained across 29 diverse tasks, from basic manipulation to complex dexterity challenges like twirling pencils, tasks that rival human skill. This rapid training is visualized within the NVIDIA Omniverse, a platform capable of rendering such detailed animations that they can test the skills of top human CGI artists. Secondly, Eureka transcends previous robotic benchmarks by generating its own reward algorithms, key to robotics training, surpassing the expertise of human specialists in 83% of tasks and enhancing robotic performance by 52%. This is partly due to the incorporation of OpenAI's GPT4, which lends Eureka the capability to autonomously develop crucial reward programs, foregoing human input. With the added advantage of Isaac Jim's GPU-accelerated simulation, Eureka efficiently sifts through potential rewards, elevating it to a superhuman status and crafting robotic instructions and potentially reshaping the future of robotics and animation. Thirdly, Eureka's ingenuity is rooted in its innovative hybrid architecture, merging high-level algorithmic ingenuity with precise motor control. GPT4 refines the robot's reward systems, while a separate mechanism uses reinforcement learning for direct robot controller training. This blend of gradient-based and gradient-free methods fosters an all-encompassing learning ecosystem for robotic training. Eureka also incorporates human feedback to fine-tune its reward alignment, a method known as in-context RL. This approach enables Eureka to operate as an invaluable auxiliary for robotics developers, combining the strengths of large-scale language models and evolutionary computation to pave new ways in tackling complex problems, and bringing the prospect of highly competent humanoid robots into the foreseeable future. In addition to reshaping robotics, OpenAI this week also heralds a new era in the realm of 3D graphics design, with its 3D GPT opening up the domain to novices, democratizing the creative process, and potentially revolutionizing how we engage with 3D design. Introducing 3D GPT, the advanced AI tool reshaping the world of digital modeling. Utilizing Blender, the renowned open-source platform for 3D graphics, 3D GPT is revolutionizing how virtual environments are created. Drawing parallels with NVIDIA's Eureka 3D, this AI model leverages its machine learning prowess to understand and execute text-based commands from users. The recent showcases of 3D GPT have been nothing short of impressive, demonstrating the AI's ability to craft detailed 3D landscapes from straightforward text directives within Blender, circumventing the complex and technical procedural generation methods that previously dominated the scene. This shift in paradigm is facilitated by OpenAI's sophisticated language models, which allow 3D GPT to interpret the natural language inputs it receives, transitioning the art of 3D creation from a manually intensive process to an intelligent, AI-powered workflow. The essence of 3D GPT's functionality is its integration of chatbot technology with Blender, functioning through a strategic three-phase operation. First, the task dispatch agent, with its comprehensive grasp of Blender's procedural generation system, efficiently delegates tasks in alignment with the user's text prompt. Following this, the conceptualization agent steps in to address any gaps or uncertainties left by the initial prompt, pondering over nuances such as the exact coloration of foliage or the reach of tree limbs. Finally, the modeling agent synthesizes all this information, scripting Python code that instructs Blender to create the envisioned 3D model. Despite its remarkable capabilities, which include reducing laborious manual coding and parameter setting, 3D GPT is still maturing and faces challenges, particularly in simulating complex textures like hair or fur, and fine-tuning intricate features like branch manipulation or color blending in 3D designs. In a parallel stride in AI-driven 3D innovation, the OmniControl model emerges as a trailblazer in generating human motion. Before its inception, encoding spatial movement within text-driven animation was fraught with difficulties, particularly in representing nuanced joint movements. Developed by a collaborative effort from Northeastern University and Google Research, OmniControl is a state-of-the-art model, adept at integrating spatial commands, overcoming these challenges and offering uniform posture representation for both input and output phases. It achieves this by translating motion into global coordinates, thereby refining control and enhancing motion fidelity. Yet, it's not just about spatial control. OmniControl also introduces realism guidance, a feature that harmonizes authenticity with precision, correcting any anomalies seen in previous models. Verified by empirical testing on platforms like HumanML3D and KitML, OmniControl stands superior to its predecessors, marking a significant advancement in the domain of AI-assisted human motion generation. If this video has been informative, please like and consider subscribing.